Have you ever really stopped to think about what happens when you press run on a piece of code? I mean, it just works, right? It feels like some kind of magic. Well, it's not magic, but it is one of the most amazing translation jobs happening in the world, millions of times a second. So let's pull back the curtain and follow this incredible hidden journey from a human idea all the way to a machine's action.
So check this out. On the left, you've got something a person can easily understand. We're just saying, hey, create something called price and make it equal to 10 plus 5. Simple enough. But on the right, that's the language the computer's processor actually speaks. It's just a long, relentless stream of ones and zeros. So the big question is, how in the world do we get from our simple, neat idea over to that electrical reality?
This gap between how we think and how a machine thinks is really the great translation problem of all of computing. We write in languages that are designed for our brains. They're abstract, they're expressive, but the machine, it needs everything spelled out in the most painfully literal way possible as a series of on or off electrical signals.
And the hero of this whole story is the compiler. Seriously, think of it as this brilliant, unbelievably fast translator. Its whole job is to take our script, our source code, and methodically convert it into a brand new script that the computer's hardware can actually execute. So, for the next few minutes, we're going to follow this compiler on its journey as it translates just our one little line of code.
Okay, so what's the very first thing any translator has to do? Well, they have to read the words, right? The compiler is no different. Its first big job is a phase called lexical analysis, which is really just a super fancy way of saying, let's figure out what the individual words are.
So the compiler starts scanning our line of code, literally character by character. It immediately throws out stuff that's only there for us humans, like extra spaces. Then it starts grouping the characters together into these meaningful little chunks called tokens. You can think of these tokens as the absolute smallest building blocks, the basic vocabulary of the programming language.
And just like that, look what happened. Our simple string of text is now this nice structured list. The compiler has figured out what each piece is. It knows price is a name, what we call an identifier. It knows the equal sign is an assignment operator. It sees 10 and 5 as numbers. The code isn't just a blob of text anymore. It's a sequence of distinct concepts.
All right, so now the compiler has its list of words, but that's not enough. It now has to ask a really important question. Do these words in this order actually form a valid sentence? Does it make grammatical sense? And this brings us to the next phase, syntax and semantic analysis. You see, every single programming language has a formal rule book, a grammar, that lays out exactly what makes a valid statement. It's a lot like the grammar you learned in school, where a sentence needs a subject and a verb. For most programming languages, this rule book is what's called a context-free grammar. It's just a very precise set of rules that says how our tokens, our identifiers, operators, and numbers are allowed to be put together.
Now, to actually use those grammar rules, the compiler does something brilliant. It builds a structure called a parse tree. And this is a huge moment. It transforms our flat, linear list of tokens into a hierarchy that actually shows the relationships between them. The compiler can now see that 10 plus 5 is a single expression, and it understands that the result of that expression is being assigned to price. The grammar checks out, it's a valid sentence.
And this whole idea of language grammar is actually part of a much bigger, beautiful concept in computer science. The Chomsky hierarchy basically classifies languages by how complex their grammar is, from the simplest all the way up to the most powerful. Our programming languages tend to live right here, at the context-free level, because it's kind of the sweet spot. It's powerful enough to be useful, but simple enough for a compiler to check the grammar really, really efficiently.
Thinking about language complexity leads us down a fascinating rabbit hole. So let's take a quick detour. For just a second, let's zoom all the way out from our single line of code and ask a much bigger question. What is the most powerful computer we could even imagine? What are the absolute, fundamental limits of what can be computed?
The answer to that question, funny enough, is this: the Turing machine. Now, this isn't a physical computer you can buy. It's a mathematical model, a thought experiment dreamt up by the brilliant Alan Turing. It's an abstract machine so powerful, it's widely believed it can compute anything that is computable. It's the theoretical gold standard for what any algorithm can ever hope to do.
And this is where things get really wild. The work of Turing, and others like him, prove that even with this ultimate, perfect machine, some problems are just unsolvable. I don't mean they're too hard or that we're not smart enough yet. I mean they are logically, fundamentally impossible for any computer, now or ever,
to solve in every case.
The most famous of these unsolvable problems is called the halting problem. It basically asks this: could you write a single program that's so smart it could look at any other program you feed it and tell you for sure if that program will eventually finish or if it's going to get stuck in an infinite loop? And the mind-blowing answer is no. It is mathematically impossible to build that kind of universal bug checker.
Okay, hold on. So if computation itself has these deep, unbreakable limits, if some things are just plain unsolvable, how on earth does our compiler ever manage to successfully translate our simple line of code and get our program to run? It works because, thankfully, our specific problem, translating price equals 10 plus 5, is very much a solvable problem. Our code doesn't ask the compiler to solve the mysteries of the universe, it just follows the rules. So, with its grammar checked and its meaning totally understood, the compiler is ready to enter its final and most transformative phase.
Now, before it spits out that final machine code, most modern compilers take a clever middle step. They create what's called an intermediate representation. You can think of it as a generic, simplified version of our program. And because it's not tied to any one specific processor yet, it lets the compiler do some really powerful housekeeping before the final translation.
And this intermediate step is where one of the compiler's coolest tricks happens: optimization. The compiler looks for ways to make our code faster or more efficient without changing what it actually does. So in this example, it sees 10 plus 5 and says, hey, I can just figure that out right now. It calculates the 15 and simplifies the code, turning 2 steps into 1. It's like a really smart editor cleaning up our work before it gets published.
And at last, we've reached the destination. The compiler takes that clean, optimized intermediate code and translates it into the specific language for the target CPU. It generates an instruction that looks something like move price 15, which basically tells the processor, move the value 15 into the memory location that we're calling price. And this instruction is then assembled into the final binary, the ones and zeros we saw at the very beginning.
And there you have it. From a simple thought in a human's head, through reading the words, checking the grammar, optimizing the logic, and finally generating the native instructions, this whole incredible multi-stage industrial process of translation happens every single time you compile code. And the craziest part? It all happens in less time than it takes you to blink.
This whole intricate dance to the bridge that allows our very human minds to talk to the cold, hard silicon logic of a machine. It's what makes all modern software possible. But you know, it leaves us with a pretty fascinating question to chew on. As AI gets more and more powerful, are we just building better and better translators, or are we actually teaching the machines to finally understand our language without needing a translator at all?